welcome you to my lecture today. Give me one second. Okay, so I want to welcome you to my lecture today. Today the focus is going to be on numerical summaries of quantitative data. I'm calling this part 2 because we started this on Wednesday. On Wednesday, we started numerical summaries of data. I remember I walk you through some measures like central tendency, the one we also call measures of center, then the measures of spread, um, the measures of position, and so on like that. So we're able to, I think I walk you through the measures of center and the measure of spread today. We're going to continue from where we stopped. Well, let me just say this as a recap to what we did the other time. Okay. The measures of, I told you we are trying to understand, we're trying to get to know our data before, the first step in any statistical analysis is for you to get to know your data. And I quoted John Tukey the other time. John Tukey in 1970 actually see what we're doing as a detective work. Okay, so we got some measures that are interconnected, that will enable us to have a comprehensive understanding of our data structure. Okay, so the first one that we call the measures of center. Okay, it's just trying to tell us, we're trying to figure how a particular data value or point that represents the rest. Okay, we did that on Wednesday, and of course, I walk you through when is the mean appropriate, when is the median appropriate, and when is the mode appropriate. Now, I also remember I touched down on the measures of spread. Okay, particularly we're talking about the range, the variance, the standard deviation, and so on like that. All of that. The essence of the measures of spread is to measure on average how far apart is the respective observation from the center. Okay, and what is new today? We want to talk about the measures of position, and I want you to see what that measure is talking about of position is that we're trying to locate the position a particular data point occupy in relation to the rest. I'm going to say that again. The measures of position, what we're trying to do is we want to identify or locate the position occupied by a particular data point in relation to the rest. Okay, so why do we need it? Of course, we live in an environment where things are changing. I know every one of you actually have a target, and the good news is we have a way to evaluate whether we have achieved the target or not. Why we're trying at times to look at the position we are in relation to others. So measures of position actually handle that. Okay, and under that measures, I'm going to talk about the quartiles, the deciles, and the percentiles. Now, I'm also going to talk about the measures of shape. Okay, anytime you hear about shape, we actually referring to distribution. We will want to see whether the distribution of the data set is symmetric. When I say symmetric, that's the normal, okay? And we want to see whether it is skewed. Is it skewed to the right or skewed to the left? Okay, and that's why we look into the skewness, okay, when we are measuring shape. Not only the skewness, we also look at the peak, the peakedness of the curve. The peakedness of the curve can actually be measured by kurtosis that I'm still going to talk about. And lastly, I'm going to talk about outliers. Okay, according to Benkamp in 1982, an outlier is a data point that is not consistent with the rest. And we need to have a way to handle that because it could be problematic, okay, to whatever model we're going to use if it is not managed. But before I go into all of this, we're left with something the other time in the other material, which is empirical rule. I thought also wanted to see what we mean by empirical rule in statistical analysis. Before now, if we want to figure out the distribution of our data set graphically, we can think of constructing histogram. We can construct a stem and leaf plot. We can even generate a density plot. There's so many ways we can look into the distribution of data set graphically. But there's something that will enable us to know whether we're dealing with a normal distribution or not. For instance, if the 68% of the observation fall within one standard deviation, because if I have a curve like this, okay, this is a normal curve, right? This is symmetric in nature. This has a double bell shape. This is an ideal distribution we're looking for. It's not as if this is the best distribution in statistics. We normally refer to this, we normally prefer to work with this because of its simplicity. Okay, because of its simplicity. Now, if I want to know whether data set, another way to figure out whether data set follow normal distribution, if about 68% of the data set fall within one standard deviation, this is the center. Okay, give me 1 second. I think I'm going to make use of my pointer right now. Now, this guy here is the center, the mu, that is the center, and the movement away from the center can be measured by number of standard deviation. So when you say sigma is the standard deviation. Now when you take a look at mu minus sigma, mu plus sigma, that is one within standard deviation. One within standard deviation, if it is mu plus sigma, that is the center, and the movement away from the center can be measured by number of standard deviation. So when you say sigma is the standard deviation. Now when you take a look at mu minus sigma, mu plus sigma, that is one within standard deviation. One within standard deviation, if it is mu plus sigma, that is one standard deviation above the mean. This one standard deviation below the mean. The area, okay, this particular area now, okay, we got 68.27% of the observation, okay, and within two standard deviation is going to be a larger area, which is this and this, okay. You know what this guy means? This guy actually means two standard deviation above because of a plus. This is a two standard deviation below because of the minus. If you want to look at the totality of the area, that will give you 95% of the data set that fall in that very area. Now, if I want to go into if you take a look at this guy, the mu plus 3 sigma, of course, that is a 3 standard deviation above the mean and 3 standard deviation below the mean. The entire area now, that is more or less nearly all the data set, or about 99.7% of the data set. Now, so in a situation where we have stuff like this, we call that 68, 95, 99.7 empirical rule. So this is one way to be able to know the distribution of the data set. Okay, now I want to go to something else, coefficient of variation. When do we use coefficient of variation? Situation where we got two sets of data and we actually want to answer a question on which of the set of data is more dispersed or less dispersed. Okay, you know, and yeah, that's why I call that a measurement of relative variability or consistency. Consistency, you have consistency if the data set is less dispersed. You have variability if it is more dispersed. And the only thing is just, since you know how to get your standard deviation and you know how to get your mean, you are good to go. Whatever you get, you multiply by 100. Now you can see two formula here. This one is for the population. When you have a population of data, you're going to make use of this one. When you have a sample of data, you actually going to make use of that. Of course, we normally work with a sample of data. We're actually going to make use of that one. Okay. S is going to be sample standard deviation, and X bar is going to be sample mean. But here, sigma is a population standard deviation, and mu is a population mean. Okay, now, like I said, we use the coefficient of variation. We can actually use that to compare the variability between two sets of data. Okay, we want to know which one is more consistent, and we want to know which one is more variable. Now, I'm going to go through an example right now. We want to compare the weight, okay, of, the infants, the new infants, and a 3-month-old children. And of course, the good news, we can actually compare that if we have their means, their respective means, and the standard deviation. Okay, when you take a look at that, a sample of newborn infant at a mean weight of 6.2 pounds, okay, with a standard deviation of 1 pound. Okay, maybe a particular researchers have taken the sample of a new infant born, and they arrive at that as the mean and that as the standard deviation, and they do the same to the 3-month-old children, right? Take a look at that. And the question now here, the question at times may not be about comparing means. I'm going to say that again. The question, I don't know, I think I'm prefer to, you can all hear me, right? Okay. Now, what I'm trying to say in a sense, the question at times may not be to compare the means, may not even be to compare the standard deviation, but maybe to compare what we're interested in is how consistent, okay, is a set of data, or how variable it is. And of course, a good measure would be a coefficient of variation. Now, all what we did, we use the formula. It's just going to be standard deviation divided by mean, multiplied by 100 for the newborn. The coefficient of variation is 60%. And you know what? Coefficient of variation is always in percentage. When you do the ratio of standard deviation to the mean, you multiply by 100. Okay, now the newborn 16%, the 3-month-old 14%. Okay, the lower CV will be, that actually means more consistency. Okay, the higher CV is more variable. Does that make sense? Okay, that's exactly what we mean. Now, I want to go into measures of partition now. The intention of this measure is to be able to locate the position occupied by a particular data point in relation to the rest. Okay, in relation, I want to know my position in relation to others. Okay, and we got 3 fantastic suggestions on how partitioning can be done. Okay, the first one, quartiles. Okay, the first idea is that, okay, you know what? If we want to do that, let us rearrange our data set from the smallest to the largest, and let's partition it into 4. Okay, let's partition it into 4. And when we partition it into 4, we are only interested in the 3 parts. We're not interested in all the 4. Okay, the first part is going to be called the lower quartile. The second part is going to be called the middle quartile. And the third part is going to be called the third quartile. Okay, that is the idea here. Okay, don't forget, we want to identify a position occupied by a data point in relation to others. Another suggestion goes like this. Okay, you know what? I'm not going to partition it to 4, but you know what? Why can't we partition it to 10? Partitioning into 10 means we're going to have 10 parts, but we're only going to be focusing, we're not going to focus on all the 10 parts. Okay. And if you want to compare this idea with the quartiles, okay, you're going to see they get some things in common, which I'm still going to talk about. Then another idea is, okay, why can't we partition it to 100? Okay, if we partition it to 100, we're not going to be, we're not going to consider all the 100 part. Okay, now let's look at the 3. The lower quartile is the same thing as 25 percentile. Also the same thing as 2.5 decile, because what is the quarter of 10? The quarter of 10 is 2.5, right? Okay, so they are all the same. So which means the middle quartile is the same thing as 50 percentile, and that is also the same thing as 5th decile. They are also in the same thing. Okay, now why do we find ourselves looking into this? There could be maybe somebody write an exam, a GRE, for those who actually come into graduate school, okay? And your score correspond to 80 percentile, okay? How can that be interpreted? Okay, the way that can be interpreted that your score is better than 80% of the student that you wrote the exam together with. Does that make sense? That's what we mean by 80 percentile. For instance, let's say I have an income, and income of $90,000 correspond maybe to 85 percentile. Okay, the interpretation of that is going to be, okay, the proportion of the household that had less or equal to $90,000, okay, is actually 85%. That's what it means, which means top 50% higher, and more. Okay, so we use all this every day in economics, in medicine, and so on, like that. Now, if you take a look at, I'm going into quartiles right now. Okay, the lower quartile, we call Q1 is also 25, percentile. And of course, I said the lowest 25% of data lies below that Q1. Okay, and of course, the second quartile that we call the middle quartile is also the same thing as the median. Okay, it's the same thing as the median. After rearranging the data set, you partition it into 2 equal half. Okay, that is the median. Okay, and we also have the upper quartile. The upper quartile is actually the upper 25%. I'm going to say that again. Upper quartile is the upper 25%, which we call 75 percentile. Okay, now, but do you know the good news here? Do you know that these measures of quartiles, okay, have a lot, perform a lot of jobs, a lot of roles? Do you know if I know quartiles, I will be able to tell about the distribution of my data set? Knowledge of quartiles also help us to know the distribution of my data set. I told you the other time, they are interconnected. Okay, now take a look at this shape right here. Can you see that normal curve? Okay, we're always going to have it this way. The Q1, the lower quartile, the middle quartile, that M means the middle quartile, okay? And the other guy is the upper quartile. And let me tell you this. If I want to know whether the distribution is skewed, or let me first start with this. If I want to know with quartiles, whether the distribution is normal, oh my God, there will be an equidistance. Q1, the distance from Q1 to this and Q3 to this will be the same the moment you see that. Do you catch that? Okay. For you to know whether you have a symmetric curve, which is an attribute of a normal distribution, okay, the Q1 and the Q3 should be equidistant to the median. Okay. But for you to know whether you have a positive skewness, the Q3 will be farther away from the median compared to the Q1. That's a positive skewness. Okay, if you want to know whether you have a negative skewness, then the Q1 will be further away from the median compared to the Q3. And I think I'm quickly going to show you that. I'm coming back to that. This is, oh, okay, never mind. That's it. That is saying something else. I'm still coming back to that. But for now, the information I want you to have, okay, it is going to be symmetric when Q1, when the lower quartile and the upper quartile, they are equidistant to the median. That's a symmetric situation where the upper quartile is farther away to the median than the lower quartile, right? That's a positive skewness. And if the other one, that's a negative skewness. Now, with this, quartiles enable us to to detect or to measure skewness. Now, do you know the combination of the quartiles can also do a job of measuring spread? I remember the other time, one of the measures of spread is range, right? We talk about range in this class. Range is the difference between the highest and the lowest of a given score. But do you know the issue with the range? The issue with the range is when outlier is present in a data set, you can't trust your range. I'm going to say that again. When outlier is present in a data set, your range as a measure of spread cannot be trusted because range is sensitive to outlier. Then what are we going to do? What is a robust way of measuring spread when outlier is present? Then we're going to use IQR. Interquartile range is going to be used. And how am I going to get IQR? I'm going to subtract the lower quartile from the upper quartile. And you know what I mean? The IQR shows the range, the middle 50% of the data falls. And therefore, that will make it to be resistant to outlier. Does that make sense? So IQR equal to Q3 minus Q1. So the Q3 minus Q1, okay, this is a measure that can be trusted when it comes to measuring spread when there's an outlier in your data set or when there's a skewness, okay, either positive skewness or negative skewness. I'm going to show you an example right now, okay? Now, let me tell you this. When data are skewed, like the other time, we compare between we use coefficient of variation, right, to compare whether data set two different want to identify data set that is more sensitive, more consistent and more variable, right? Okay, now we can only use the coefficient of variation to do that, in a situation where the two data set that I'm comparing is normal. Do you know the formula for the coefficient of variation? The standard deviation over mean. You are using standard deviation over mean. Don't forget the mean and the standard deviation, they are also sensitive to outlier. So therefore, if you want to compare two sets of data, you need to also understand the distribution of the two sets of data for you to compare, for you to know what you are going to use in your comparison. Now, what I'm trying to say, if this set of data set is normal, this set of data set is normal, and I want to compare variability, of course, I'm actually going to use coefficient of variation. But what if in a situation where the data set, they are skewed? Then I'm going to use IQR. Now I'm going to use example from salaries. Example from salaries of NBA players. Some are in the Eastern Conference and some are in the Western Conference. And of course, these are analysis in R. Of course, in this class, you're going to be using R. Okay, very crucial. Make sure you attend our lab. The next assignment you're going to see, you're actually going to use the knowledge of R. Okay, very crucial. Now, because of that, we have some 5 numbers summary. Go ahead. You say what? Yeah, question about outlier. Go ahead. That's that. Why can't we cancel it? Why can't we discard it? That's a very good question. This argument came up when I was doing my PhD work because I work on outlier, and some people say, why can't you just discard an outlier? You can only discard the outlier that you know the source. If the source is through erroneous imputation, maybe you are collecting data, right? And maybe data is supposed to be 15, and you mistakenly added 3 zeros, okay, you can remove that. But an outlier that is a genuine observation cannot be removed. For instance, I conduct exam in this class, okay, and everybody score 90, 99, and somebody scores 0. And I want to calculate class average. Am I going to remove the 0? I'm not going to, because it's a genuine student. So I have to look for a statistical methodology, okay, that is robust, like median, if I want to get the average. Have I answered your question? That's a nice question. Okay, now we got 5 number summary, okay, minimum, maximum, and the 3 quartiles. We call that 5 number summary. Okay, now if you take a look at this, if you understand if you know the name of your data, you do summary, it's gonna give you all of that. In this course, you are not computing whenever I give you assignment, you don't do that manually. We don't have time for manual computation. You're going to use R. R is very easy. Okay. Now, I need you to take a look at the IQR for the two. Why am I using IQR? To compare variability, because the data set that I have is skewed. Go ahead. How do we calculate what? Oh, okay. How do you calculate the Q1, the word brother? We have a coding now. Very simple code is going to return all of that. Now, take a look at this. When you have your data set, you just do summary. Do you see? Look at that code. Look at what I'm showing now. Summary. Okay. The name of my data set here is salary. I want to focus on the conference because there are 2 conferences in my data set. Okay. Okay. So for the Eastern Conference, you can see E, arrow will automatically display, you're actually going to display minimum. You see first quartile, the median, the mean, the third quartile, the maximum. Do you see that? You don't need to use your calculator. With a simple coding now, summary into your data, it's going to give you that. My TA will walk you through that. Have I answered your question? Okay. Okay. Now, I wanted to compare these two now, and I gave the code for the two, right? Now, the one that have the higher IQR is the one for the Western Conference. The one with the higher IQR is actually the one that is more variable. Does that make sense? The one with the lower IQR is the one, and that was why I said, look at that. Salaries are more spread out in the Western Conference, okay, compared to so if you take a look at what I have here, more spread out. This one means more spread out because it's greater than that. Does that make sense? Okay. Now, another thing you can take note, you can compare the means. One, if you look at the Eastern Conference, can you see 98? I think that should be 98 million something, right? Okay, this guy here. Can you see this one? That is the mean for the Eastern Conference. Can you see the mean for you also see the mean for the Western Conference? That is what we're interpreting here. Okay, take a look at that. Another important measure that you need to understand that we can use quartiles, the idea of quartiles, the 3 quartiles with the minimum and the maximum to generate a box plot. And what is the significance of box plot? The box plot is going to do a lot of job. This is a box plot. What you're seeing right now is a box plot. We construct box plot from 5 number summary, the 3 quartiles, the minimum, and the maximum. Let me tell you this, the box plot will enable you to know the distribution, whether it is skewed or not. The box plot will enable you to know how it is spread out. Okay, the box plot will enable you to compare distributions among groups. Now, the tail here, if you take a look at this guy, the minimum, this guy here is a Q1, this guy here is a Q2, that is a Q3, and this is the maximum. And let me tell you, with the box plot, any numbers outside this box plot could be regarded as a potential outliers. Does that make sense? Go ahead. Okay, so this one, the minimum, Q1, which is the lower quartile, Q2, which is the median, Q3, which is the upper quartile, maximum, the tail, a minimum, maximum, anything outside that should be regarded as potential outliers. Now you know what I want to do now. Take a look at this. That's a symmetric. Why is it symmetric? The Q1 and the Q3, they are equidistant, right, to the median, right? Why is this one right skewed? Look at the distance of the Q3 to the median is farther than the distance from the Q1 to the median. That's a right skewness. I told you, this, the box plot also going to enable us to investigate that. This is left skewed. Can you see that? So in case you see a box plot can tell you the idea, can give you the idea about the distribution too. And that's why box plot is very essential in descriptive statistics. Okay, go ahead. No, it's the same. Oh, no, it's just for simplicity. Because lower quartile is the same thing as 25 percentile. So middle quartile, here, Q2, median, is the same thing as 50 percentile. We're using quartiles here. The quartiles are very easy to use compared to, but if you want to talk about in interpretation, like I mentioned something about performance the other time, your score corresponds to 85 percentile. Okay, we use more of percentile when it comes to stuff like that. Not more accurate. Simplicity of interpretation, because they are all the same. Does that make sense? Go ahead. How do I know what? I need to. Okay, for this course, this is just what we need to do. Okay, if you want to generate a box plot, okay, use quartiles. It's not as if percentiles cannot be used. It's not as if decile cannot be used. But let me tell you this. If you want to use percentile, it has to correspond to the quartiles. Q1 has to be 25 percentile. Q2 has to be 50 percentile. Q3 has to be 75 percentile. If you want to use decile, it also needs to correspond. Go ahead. Oh, okay. You know, that's a different one. It's like we are looking for different options for us to be able to say, okay, this is normal or not. Another way of knowing it is normal is when empirical rule hold. If empirical rule does not hold, it is not normal. Does that make sense? And that will take us to Chebyshev rule. Okay, but not now. Okay, now how do I draw a box plot? Very easy now. Okay, my T is going to walk you through that. Now take a look at this. Um, if you take a look at this example, Okay, in this example, we collect data set from 98 students about the cost of their haircuts. Okay, both female and male. Okay, now this is the overall. This is the overall bus plot of the data where you look at all of them, 98 students. Okay, you can see the distribution. Okay, skew, right? To the right. Can you see that? Okay, now this is we can have a side-by-side bus plot where we're comparing female with male. If you take a look at what you are seeing here, you're going to see that okay, this is the reason why my wife spent more money for here, you know. Like, look at male here, look at the median, compare the median here to the median here. Can you see that? Yeah, go ahead. You see what? No, it's at times it could be it's not visible in the situation where it means the median is very close to the other one. So that's why you don't see that. Yeah. Which one? Oh, you mean, yeah. So now, and that is why we actually take a look at what we wrote. That's our observation. Overall cost is right skill. Women spend more than men. How do I know? We compare the median. Okay. Women are more spread out. Okay. You look at least one outlier. You know, I saw like that. You write your observation. Okay. Now, looking at the IQ how because of my time, you know, at time we can say Q3 minus Q1, or you can say upper quartile minus lower quartile. They made the same thing. And let me also tell you this. Imagine you draw something like this. What are those points? We call them outliers. They are potential outliers. Those points outside the box. So box plot can also be used to detect outlier. Go ahead. Yeah, I know it was invisible. That was why I showed this. You know, that picture wasn't that visible. Okay. But a clear picture will actually show. Do you see that? Okay. Now, another thing. Do you know we use measures of quartile to detect outlier? How can it be used? Now, if you know your Q3 and Q1, if you know the upper quartile and the lower quartile, we have a threshold 1.5. That very threshold 1.5 was chosen in a way to make sure there's a balance. We don't call all high values outlier or all low values outlier, but we're actually going to identify unusual high values or unusual low values. Now, if you take a look at the first one, if you take a look at this guy now, if I have my lower quartile and I multiply 1.5 by IQR, I subtract. If I go back to the data set, any data below that value is an outlier. If I compute this guy, the one for plus, okay, whatever I get, if I go to the data set, any data point above is an outlier. Okay, so take a look at that. And take a look at this. We can also have several comparisons of groups. Here we're talking about income by highest degree. Okay, no high school, some high school, and so on like that. And you can see the average, the median. Okay, it's not the same. You can also talk about the skewness and so on like that. Okay, you can compare all of that. Okay, the next thing I want to talk about is the measures of shape. When we talk about measures of shape, we talk about skewness, we talk about kurtosis. What do we mean by skewness? You know about skewness. That measure the departure of the distribution of data from normality. We're not only interested in the departure from, in the departure from normality, we're also interested in the pickedness. The pickedness. Okay, the pickedness, the kurtosis measure the pickedness. What I'm going to do right now, I'm going to tell you the threshold for normal distribution. Now take a look at this curve. We all know when mean is greater than the median, and median greater than you know it's a positive skewness, right? We did that on Monday. Now, I'm giving you an example of data set that could be asymmetric, you know, positive skewness. Income, contribution to candidate population of countries, they may be right skewed. But let me tell you this, if you have data set, okay, you really want to know about the distribution, of course, construct histogram, construct or stem plot, or whichever maybe box plot and so on like that, you will be able to know. Now for our asymmetric, okay, this one to the left, Okay, the negative skewness, okay, GPA of University of Minnesota student, skew to the left. Okay, things are changing. There's possibility. The student that we have right now, their GPA may not skew to the left. Okay, we got to investigate. Now, I want to talk about kurtosis now. We know skewness is a balance, but the kurtosis deal with the pickedness of the curve. Now, which one is the normal pickedness, a normal distribution should have is this one, the one where k equal to 3, which is a moderate one. That is a moderate one. We don't want it to be too low. When it is too low, the kurtosis is less than 3. It is called platykurtic. When it is too high, it is called leptokurtic. The one that is too high, we normally experience that in financial data. Okay, it's they have financial data has a high kurtosis, and therefore you cannot use a model in statistics that have the underlying assumptions of normality to figure it out. Okay, you have to know that. So take a look at that. Mesokurtic, when k equal to 3, that is for the normal. Okay, when it is less than 3, greater than 3, that's a problem. Okay, now take a look at this guy now. Now, in terms of shape, let us use a threshold. Okay, for normal shape, skewness is a 0, kurtosis must be 3. Does that make sense? That is for the normal. And what you see here, you're going to be wondering, how do we actually graph this? What function do we use? This is the function. This is given by Ronald Fisher. Okay, that is a normal distribution function. Then what are the data set in real life that we can use normal distribution to model a data set on intelligence quotient, on SAT score, height, and so on? They don't have skewness, and the kurtosis is very close to 3. Now, the last thing I'm going to talk about today before I go, the Z-score. Please, I need you to pay attention. This is very, very crucial. The measures of partition will tell us the position a data point occupy in relation to others. But Z-score will compare the value of a particular data point to the average of all the data points. In this class, maybe I scored 90, and I want to compare my value, my score with the average of the class. That average of the class include my data. Does that make sense? Okay, now that is what we call Z-score. Okay, and let me tell you, you know what Z-score implies? Z-score implies the number of standard, the other time I was talking about the number of standard deviation away from the mean. If I want to know if my Z-score is negative, that is below the mean. If my Z-score is positive, that is above the mean. Does that make sense? Please take a look at this. Statistics is a story that goes on and on and on. If you try to understand the intention that we have behind the scene, oh my God, you're going to fall in love with statistics. Now, take a look at this data set now. Okay, this is a repair course on luxury vehicles, repair course. Okay, take a look at that. Now, when you take a look at this, we use R to find some stuff, and we find the mean, we find the standard deviation, and we want to know, for instance, we want to compare the cost that we spend on a particular vehicle, Volvo S80. Okay, this guy is the mean of all the costs. The bottom one is the standard deviation. 4194 is the cost for the Volvo. Okay, let's go to the Volvo. Where's your Volvo? Oh, it's right here. Can you see that? We want to compare that cost with the average. Okay, now this is what we do. Oh my God, this is giving 2.67. The meaning of that 2.67, it means that is a number of standard deviation above the mean, above the center. 2.67 above the mean. That is what it means. When you have a negative, it means below that number of standard deviation below. So take a look at that. And that is why we said, since most of the data will be within, don't forget, for normal distribution, we expect 99-point-something% of the data to fall within 3 standard deviation, right? And what is happening now? These guys still fall within. Therefore, I said since most of the data will be within that, this is an extreme observation. Okay. Now, another thing, take a look at this guy here. I measure the height of something. This is a red flag. How am I ready to know? I can calculate the z-score. Okay. If I want to detect an outlier, apart from using IQR, I can also use we can tolerate 3 standard deviation. Anything outside, whether 3 below or 3 above, is an outlier. What's happening here? This is more than 3, it's an outlier. Now, take a look at this, showing an outlier. You see that particular data point is not consistent with the rest. And what are we going to do? We don't just throw away. Okay, you have to read this. So this answer your question. Okay, outlier from, so that you see that it could be a legitimate focus of inquiry. Okay, now I want to walk you through. If there's no outlier in the data set, what happened? The mean, the median, the mode, they're very close, right? I want to put an outlier now. Oh my God, I just put 400 now. Look at the mean. The mean is not a good measure when the outlier is present. Look at that. Okay, and if mean is not a good measure, you cannot trust standard deviation too. Okay, now this is the example that I gave you the other time. These are student score. Somebody scores 0. Am I going to throw 0 away? No way. Okay, what happened? The 0 bring down the mean. What are we going to trust? We're going to trust the median. Does that make sense? Okay, I put exercise here. Do I still have time? Okay, I still have 5 minutes. Now, the percentage of the US population without health insurance coverage is shown below with a sample from the 50 states and the DC for both 1997 and 1998. Watch out. We give you a table of data. We're going to ask you, put the knowledge you acquire into practice. The knowledge of measures of center, the measures of spread, the measures of shape, and the skewness. Now take a look at it. Describe the distribution of state percentages of Americans without health insurance coverage in 1998. Be sure to employ both measures of central location, expansion. Now take a look at this. This is the table. Okay. This is the table 1997 and 1998. Okay. And look at the analysis. How many states? 51 counts represent the numbers of states. Mean, we get the mean, we get the median. Can you see that? Here, the mean is greater than the median. You should be expecting a positive skewness, right, to the data. Okay. Now, the standard deviation is that, and these are the minimum, maximum, the first quartile, the third quartile, the skewness. Don't forget, the skewness of a normal distribution should be 0, right? This is not 0. Okay. Now, you can see what I wrote. This distribution is slightly skewed. Let me tell you this. At times, if you take a look at this skewness, it's not far from 0, even though it is skewed, but it is slightly skewed. If you look at the mean and the median too, they're very close. Okay, we can still approximately use normal in a situation where the skewness is just little. It's not significant. Does that make sense? Okay. Now, I said, right, as evidenced by the fact that its mean exceed the median. Okay, you can see, I don't just say it's positively skewed. I have to give the reason why it is. Then the standard deviation of that, there's a lot of things to talk about. Oh my God, that's going to be the end of this statistical party. Is there any question before I go? Any question? Okay, go ahead. Okay, you know what you're going to do because of the noise? You can come to me. Yeah. Okay. Now, what is the question? You want to do one? Oh, the textbook. Do you check the syllabus? Do you see the recommended textbook? I saw the textbook. Yeah. Yeah. You can read all of that. You can read the coursework. You can also read the other one too. Yeah. Yeah. You're welcome. Do you have to memorize those like formulas, or are they gonna be? Oh, they're gonna be now. They're gonna be now. I've been writing them down, but yeah, you're gonna. Oh, you got. I'm gonna allow sheet. Anyway. Yeah, in exam before exam, there's gonna be a lot of information. Yeah.
I was just wondering, how is the skewness calculated?
Oh, how is skewness calculated? Okay, we have a standard formula for calculating skewness, but you know what? We're gonna do that in R.
Okay.
Yeah,
So,
but there's a formula for it.
okay.
But we know how you actually, that's what my TA is going to walk you through.
Okay.
Yeah.
Alright, thank you.
You're welcome.
I just wanted to inform you that like 3 days a week for stats. Right before this, 15 minutes ago, my other class ends. It takes me like 16 minutes to walk here,
Oh,
so I'm probably gonna be late like every
I
time by like
understand.
2
I
minutes.
understand.
Okay.
I'm flexible. That's no
Okay.
problem. Yeah.
Thank you.
You're welcome. Yep.
Do you calculate the K or
Oh, the kurtosis.
Yeah.
Yeah, you're gonna also do that in R.
in R?
We have a code that will just give you all of
So
that,
just
all
give
the
you all-
basic.
Okay.
Yeah. You're welcome. Okay.
So you said something about like that's over like the mean.
Yeah, the standard deviation over mean times 100. That's question.
What's the S? The sample of like what?
Sample standard deviation. Sample standard deviation. We want consistency. Consistency is a prerequisite for reliability. Yeah.
Standard deviation.
Yeah, that is calculating the coefficient of variation. It's like you're putting into consideration, the mean and the standard deviation. You're looking at the ratio. Let's assume that the standard deviation is 0. What is going to happen? The CV will be 0, right? That's a perfect environment. That's never going to happen.
So that is the cost of this specific thing
That we are considering.
That's the mean.
That is the standard deviation. Yeah.
And if it's always within the standard deviation,
Yeah.
then it's not an outlier. But if it's above it,
No, if it is within the 3 standard deviation, we're going to say there's no problem
okay.
about outlier.
But if it's above it,
But if it is either above, if it fall outside,
yeah.
Falling outside could be above it or below it.
Yeah.
It has to be a potential outlier.
Okay. So standard 3 deviation. If it's above or below, it could be a potential outlier.
Exactly.
Okay.
Mhm.
Thank you.
You're welcome. Yeah, how are you?
I'm good. How you doing, man?
I'm good.
I'm starting to get a little confused with like the lectures this week. I tried to find your office hours in Canvas, but I couldn't.
Oh, it's on Tuesday from 10 a.m. to 12.
Okay.
And it's through the Zoom.
Okay.
The link is shared on the canvas. So all you just need to do, you can be anywhere in the world.
Okay.
Just click on the Zoom.
And then for your TAs, because I was gonna do a Zoom meeting with your TA. Does she only go over like the R stuff, or does she also go over some lecture stuff too?
No.
Just
You know
R?
what the TA is going to do is just, or whatever we do here,
Yeah.
is actually going to walk you through how to implement that with R software. Yeah.
Okay, cool. And you said Tuesday.
Mine,
Yeah.
Tuesday from 10 to 12, tentatively for now, because I've been getting some kind of report from cerebral conflict.
Okay.
So, and I think I'm trying to adjust. So, but for now, tentatively,
Okay, and if I can't make that time, is there any way I can like set up a meeting with you?
Yeah, try.
Okay.
Yeah, try.
Send me an email.
We're gonna see what work out.
Okay.
Gonna work something out. So,
Okay.
Yeah.
Thank you, man.
You're
Have a good day, man. Have a
And
good weekend.
too.
Appreciate it.
Yeah. Okay.
You can go.
Yeah. How are you?
Good.
Yeah.
How are you?
I'm good.
Question with the box and whisker.
Oh, the boss and whisker. Yeah. Go ahead.
The whiskers, you said they were the minimum, the maximum, but there were outliers outside.
Yeah.
How would you determine if that's an outlier?
Yeah, the moment you generate the plot, the boss automatically gonna show. And
So because the
and
whiskers were the max and the minimum, but the outliers were outside.
yeah, because it's when I first saw that, I was like, how can outlier be aside? When I already have the minimum and the maximum. You that's what I mean. So, but that is the beauty of a box plot. Anything that doesn't fall within the minimum and the maximum, okay, just like what I show the other time, where you saw some point outside, okay, it's their potential outlier.
The software will just do that for us.
The software will automatically, if you try to do that with R, or manually, because we normally work with a large volume of data set, and that's why we're looking for something that we aid our computation. So that's why we're using software. Yeah.
Thanks.
That's a very good question. Yeah.
What does LQ and UQ stand for?
Yeah, AQ is the lower quartile,
Mhm.
which is Q1.
Okay.
We can also Q1, and
Okay.
yeah, the other one is your UC is your UQ is your upper quartile.
So it is minimum, then first quartile, median, second
third quartile
And the
and
maximum.
maximum.
Yeah.
Okay, then the last two, measure of quartile and measure of spread, it doesn't seem to be in your handout notes. One
Yeah,
PDF that you are
Yeah, that's why we also talk about textbook.
yeah, that's the textbook which you get through coursework is the
Yeah,
one we're supposed to
exactly.
view,
Yeah,
right?
yeah.
And one question. Okay, I don't remember. I think that's all I needed to ask.
Okay. And the one, if you remember later, you can send message to me.
Okay.
Through by email. So
Okay.
okay.
So did you by any chance get the mail I had sent you earlier? I told you that I missed one class.
Yeah. There's no issue at all because I record my lectures.
Mhm.
And if you go to the canvas right now, I've updated. You're gonna see recordings to except this one today. The one today will be ready like maybe in the evening or tomorrow. So yeah.
Okay. Thank you.
Okay, you're welcome. Have a good day.